So let's now talk about the sampling distribution of the sample mean x bar. Suppose we have a variable x, right, with mean mu of x and standard deviation sigma of x. Okay, so if you think about the example we talked about earlier, think of x as being the height variable. Think of mu of x as being the average height of all 7 billion people. Right? And then think of sigma of x as being the standard deviation of the heights of all 7 billion people. Okay. Suppose that from this population of x, we take samples of size n. Right? So what we want to do now is we want to study the sampling distribution of sample means of size n. Okay. In other words, we want to know the distribution of all possible sample means of size n. Okay. Now it can be proven that the expected value of all the sample means, which is equal to the mean of all the sample means, equals the population mean. So the mean of the original variable x. Okay. Second, it can be proven that the standard deviation of all the sample means is equal to the standard deviation of the underlying variable x divided by the square root of the sample size. Okay. Where n here is the sample size. And typically we refer to the standard deviation of all the sample means as the standard error of the mean. Okay. Now when it comes to the distribution shape, we're going to have two cases. Okay. First off, if we know that the underlying variable x is normally distributed, then all the sample means x bar are normally distributed. Okay. Now if we know that x is not normally distributed, or if the distribution of x is not known, okay, then we use what's called the central limit theorem. Or CLT. And the central limit theorem says that if the sample size is sufficiently large, then sample means x bar are normally distributed. Okay. Now you may be wondering how large is sufficiently large, right? Typically when we say that the sample mean is sufficiently large, we're talking about when we say sample size is sufficiently large, we're talking about sample size of being greater than or equal to 30. Okay? So let's do a quick recap. We have a variable x with the population mean of mu x and population standard deviation of sigma x. Okay? We take samples of size n from this population. We want to know the sampling distribution of the sample means of size n. It can be proven that the mean of all the means, the mean of all the sample means, is equal to the population mean of the underlying variable. Okay? It can be proven that the standard deviation of all the sample means is equal to the standard deviation of the underlying variable divided by the square root of the sample size. Okay? And the standard deviation of all the sample means is typically referred to as the standard error of the mean. Okay? Now, when it comes to the distribution shape, if we know that the underlying variable x is normally distributed, then the sample means x bar are normally distributed. Okay? If we know that the underlying variable x is not normally distributed, or if the distribution of x is not known, then we use the central limit theorem, which states that if the sample size is sufficiently large, then the sample means are normally distributed. And by sufficiently large, we're talking about sample size of greater than or equal to 30. Okay? Now, I think the best way to understand the central limit theorem is to look at this figure. Okay? So in this figure, on the first row, we have 3 random distributions. Right? Think of them as the distributions of the original variable x. The first distribution here looks like a uniform distribution, right? The second and third distributions don't look like things we've seen before in the course. Okay. Now on the second row, we have sampling distributions of sample means of size 5. Okay. Again, this means that for each of these cases, we calculate the averages of all samples of size 5 and plot the distribution of those numbers. Okay. Notice how there's not a pattern when it comes to the distribution of sample means of size 5, right? They're completely different distributions. On the third row, we have sampling distributions of sample means of size 30. Okay? See, now things get interesting here, right? The sampling distribution of the means of size 30 or look roughly normal, right? So even when the underlying distribution is not normal, as long as we have a large enough sample size, the sampling distribution of the sample means will be normally distributed. Okay?